We've all been wowed by the magic of large language models. They feel like a glimpse into the future. But what happens when the magic has to work for 1 million users every single day? Taking a simple LLM from a cool demo to a scalable, reliable system is a massive engineering challenge. The truth is, without the right operational strategy, your groundbreaking AI is just an expensive experiment. That's where LLM Ops comes in. Think real-time fact-checking, multimodal capabilities, and the rise of autonomous agents. In this video, you'll learn how to go from a single model to a full-fledged system, build production-ready LLMs that don't just work, they scale. Watch now to get the blueprint for your next big AI project. If you're still using old FAANG prep guides, you're already losing ground. The rules have changed, and this free AI playbook shows you what's really being tested in modern FAANG interviews, insider strategies, hidden evaluation matrix, a 90-day mastery plan, the exact playbook successful candidates are using right now. Everyone's grabbing it, don't be the one left behind. Link in description.
My name is Pranjal Joshi. I am a machine learning engineer and an AI consultant. My background is in building and deploying enterprise-grade AI systems from the ground up. In my current work, I've built an Gen AI platform that leverages self-hosted open-source LLMs with features like RAG and text-to-SQL, which has successfully reduced operational costs by a lot in the fintech domain. Currently, I'm building a stealth healthcare startup that uses advanced techniques like RLHF for diagnostics. Everything that I'm sharing today comes from the practical, hands-on lessons learned while making these complex systems a reality. So here's a roadmap for today. First, we'll start by architecting a production LLM system. We'll begin with the simplest possible setup and build on it layer by layer, adding all the essential components for a modern application. Next, we'll cover observability and user feedback. Once our system is built, we need to know how to debug it and create loops for continuous improvement. Then we'll tie it all together with a practical case study, where we design an AI tutor from the initial concept all the way to a production-ready design. We'll finish with key takeaways and a conclusion followed by a live demo in the notebook where you can see those concepts in action. This is a quick recap of MLOps. MLOps is essentially the engineering culture and practice that unifies ML development. That's the dev side, and with ML operations being the ops side. The goal is automation and monitoring across the entire lifecycle of an ML system. That includes integration, testing, releasing and deployment, and infrastructure management. So MLOps ensures models don't just work in notebook, but they work reliably, reproducibly. Now, when we move to large language models, MLOps isn't alone enough. We add a new layer, what we call LLM Ops. We also need to think about the broader M system design. LLM Ops focuses on the model side, experimenting with the foundation models, designing and managing prompts, doing supervised fine-tuning, monitoring model behavior, and evaluating generative outputs, which is much trickier than evaluating traditional models, by the way. But beyond that, there's LLM system design. This is the bigger picture, designing the entire end-to-end application around LLMs, chaining multiple LLMs together, grounding them in domain-specific or internal data, and tracking history or context across interactions. So you can think of it this way. LLM Ops is about managing the model. LLM system design is about managing the application that uses the model. Both are critical if we want to deploy LLMs in real-world production-grade systems. All right, so let's talk about how an AI application goes. At its core, the simplest setup is just what you see here. A user sends a query, it goes to the model sends back a response. That's it. There's no extra context, no safety nets, and no optimizations. But to build something truly powerful, we need to add more layers. Think of it as a journey with a few key steps. First, we enhance the context by giving the model access to external data and tools. Next, we put in guardrails to protect our system and our users. Then we might add a model router and gateway to handle more complex tasks and beef up security. After that, we optimize for speed and cost, usually with caching. Finally, we add complex logic and actions to kind of really unlock the system's potential. Now, this is a common path, but it's not set in stone. The right order really depends on your specific application's needs. We'll also cover essential pieces like monitoring and orchestration as we go. So the first step to expanding our AI platform is to enhance the context we provide to the model. Think of it like this. Context is the background information the model needs to give a smart answer. It's essentially feature engineering for foundational models. We build this context in two main ways. First, through retrieval. This means pulling in data from text documents, images, or even tables. Second, by using tools, these are APIs that let the model actively search the web or check the latest news, weather, events, etc. Now, all the big providers like OpenAI, Claude, Gemini support this, but they all do it a bit differently. They have different limits on what you can upload, what tools they support, and how their retrieval algorithms work. A specialized system might let you use a massive database, while a generic API might let you only upload a few files. So, we build our architecture. We need to be smart about how we construct the context because it directly impacts the quality of our final output. So now that our model has the right context, our next critical step is to make it safe. That's where guardrails come in. Think of guardrails as a safety bumpers for our AI system. They protect both us and our users by monitoring the data going in and the responses coming out. First, let's talk about input guardrails. Their main job is to prevent two key risks. First, stopping malicious prompts that could compromise a system, and more commonly preventing sensitive data like a user's phone number or our company's internal secrets from being accidentally leaked to an external model API. We can do this by automatically detecting and either blocking or masking that private info. Next, we have output guardrails. This is our quality control. They catch model failures, which can range from either quality issues like a badly formatted response or a factual hallucination to security risks like toxic content, brand damaging statements, or leaking private information. When a failure happens, we can handle it in a couple of ways. Often, a simple retry works, since the model might give a better answer on the second try. For trickier cases, we can even fall back to a human operator. But there is a trade-off. Guardrails add processing time, which means more latency. It's a constant balance between being perfectly safe and being perfectly fast. As you can see in the diagram, guardrails become a fundamental layer that sits around our model API, ensuring everything is checked. So as you can see over here, this is an example of how you mask your PII while you feed it to your model context. And then you have that logic offline so that you can reuse the same logic to kind of reverse engineer into the original solution to ship it to the user. As our application gets more sophisticated, we'll likely use more than one model. To manage this complexity and control costs, we introduce our next component, the model router. Think of the router as a smart traffic cop for AI queries. Instead of sending every single question to our most powerful and expensive model, the router intelligently directs each query to the best possible destination. This approach gives us two huge benefits. Better performance. Over here, we can kind of use specialized models for specific tasks. For example, one model for technical troubleshooting, another for billing questions. A specialist is often better than a generalist. Cost savings. Simple, common questions can be routed to, for example, to cheaper, faster models, saving our expensive, high-power models for the really tough problems. So how does it actually work out? The router uses what's called an intent classifier to figure out what the user is trying to do. Based on that intent, it sends the query to the right place. If a user asks to reset their password, it can route them to an FAQ page. If they have a complex billing issue, it can route them directly to a human agent. If the query is out of scope, like a political question, the router can use a pre-written response, saving an expensive API call. As our architecture diagram shows, the router becomes the crucial decision-making layer, making sure we use the right tool for the right job every single time. Okay, our router is sending queries to different models, but that can get messy. How do we manage all these different APIs from OpenAI, Google, and maybe even our own models? So the answer to that is a model gateway. Think of the gateway as a universal adapter or a single front door for all your AI models. It provides one unified interface to talk to any model, no matter who provides it. This has several key benefits. First, it makes maintenance much easier. If an API changes, you only update the code in one place, the gateway. Second, it gives you centralized security and cost control. So instead of sharing API keys, you create a single point of access where you can manage permissions, monitor usage, and prevent budget overruns. And finally, it makes your application more reliable. If your primary model fails, the gateway can automatically reroute the request to a backup, ensuring your app stays online. Because all requests flow through it, it's also the perfect place for logging and analytics. So let's see how the gateway changes our overall architecture over here. As you can see, the gateway now effectively replaces the original model API box we started with. Our input guardrails send requests directly to the gateway and it handles everything from there. The complexity of our router and all the different models are now neatly tucked away behind this simple interface. This means the rest of our application doesn't need to know or care about which specific model is being used. It just talks to the gateway. So we've now built up our system with context, guardrails, smart routing, and a unified gateway to manage it all securely and efficiently. Okay, so our system is getting more powerful, but with more power comes the potential for higher latency and cost, right? Our next step is to make it faster and more efficient using a classic technique, that is caching. The idea is simple. If we've already done the work to answer a question once, let's save the results so we do not have to do it all over again. We'll look at two main ways to do this. Exact caching. First, there's exact caching where this is the most straightforward approach. If a new query comes in that is identical to one we've seen before, we just pull the saved answer directly from the cache. This is fantastic for frequently asked non-personal questions. Of course, we have to be very careful about what we cache. We should avoid caching user-specific or time-sensitive queries to prevent performance issues and, more importantly, accidental data leaks. Then comes in semantic caching. Instead of looking for an exact match, this method looks for a query that is semantically similar, one that means the same thing. For example, it would know that what's the capital of Vietnam and what is Vietnam's capital city are the same question and reuse the answer. This can really increase how often our cache is useful. However, this power comes with a trade-off. Semantic caching is complex, can be slow since it requires a vector search, and if it's not tuned perfectly, it risks returning the wrong answer. As our diagram now shows, the cache becomes a critical optimization layer. Before our system does any heavy lifting, it first checks the cache, saving us time and money by intelligently reusing previous work. So far, our architecture has been fairly linear. A query comes in, goes through the steps, and an answer comes out. Now, we'll make our system smarter by adding agent patterns. The key idea is to move beyond a simple one-shot flow. With agent patterns, a model's output isn't always the final answer. Instead, it can be used to decide what to do next, creating complex workflows with loops and conditional logic. A classic example is a feedback loop. The system generates an initial response, it then evaluates that response and realizes it's incomplete or needs more data. This triggers another action like a web search or a database query. Finally, it combines the old response with the new information and tries again, generating a much better, more refined answer. As you can see in this diagram, we've added a crucial feedback path. This allows the system to think, reflect, and iteratively improve on its own work, tackling more complex problems. Now let's take this agent concept to the next level by giving our system the ability to perform right actions. A right action is when the model doesn't retrieve information. It actively changes something in its environment. This could be anything from composing and sending an email, placing an order on a website, or even initiating a bank transfer. This transforms our application from a simple information provider into a powerful assistant that can take real action on a user's behalf. However, this is critical. This also exposes our system to significantly more risk. Giving an AI the power to directly change things must be done with utmost care and extremely robust guardrails. As our final architecture shows, the system can now act on the world, but you can also see that our system has become quite complex. With all these new components and feedback loops, it becomes much harder to debug when something goes wrong. This brings us to the next essential topic, observability and monitoring. So we've just discussed about how our systems have become much more complex, which makes them a real challenge to debug. What you're looking at is a request trace from a tool called Langsmith. It gives us a transparent step-by-step view into the agent's thought process as it works through a problem. On the left, you see the user's query. How many points was scored in the 2023 Super Bowl than in 2022? Now, the really interesting part is the run tree on the right. it isn't just one single call to an AI model. You can see the agent's entire chain of reasoning. First, it realizes it needs information, so it uses a search tool to find the score of the 2023 game. Then it does another search to find the score for the 2022 game. Only after it has gathered all the facts does it perform the final step, using the model to synthesize the results and calculate the final answer. This kind of detailed trace is invaluable. If the final answer was wrong, we could look here and pinpoint exactly which step failed. We can also see how long each step took and how many tokens it consumed, which is critical for optimizing performance and managing costs. Ultimately, tools like this turn AI's black box into a glass box, making it possible for us to build, debug, and confidently run the complex agentic systems we've just designed. Beyond what users type, we can get incredibly valuable feedback simply by observing their actions. One of our most common actions is regeneration. When a user clicks the button to get a new or different answer. Now, regeneration is a signal, but on its own, it can be a bit ambiguous. Does it mean the user hated the first response? Or were they curious and wanted to see another option, which is kind of common too for creative tasks? Maybe they were just double checking the model's consistency on a complex query. To get a clearer signal, we can combine that implicit action with a direct explicit question. That's exactly what you see in the example here. After a user regenerates a response, the application follows up and asks a simple question. Was this response better or worse? The simple interaction is incredibly powerful. It provides kind of a clear and comparative data directly from the user. This better versus worse feedback is the perfect fuel for advanced models like preference fine-tuning, which is how we continuously train the model to better align with what our users actually want. So now we know that we need to collect user feedback, but what's the best way to do it? This is all about feedback design, being strategic about when and where to ask it. The golden rule is that feedback options should always be available but must be non-intrusive. They shouldn't get into the way of what the user is trying to do. We can ask for feedback at key moments. For example, right at the beginning to help calibrate a new user's experience. But the most critical time is, of course, when something goes wrong. However, the most powerful feedback systems don't let users report a problem. They empower users to collaborate with the AI to fix it. A perfect example of this is the imprinting feature for image generation, which is what you see here. First, the user generated an image of a cat but wasn't happy with its expression. Instead of starting over, they simply selected the specific part they wanted to change, that is the cat's face. Then they gave a new targeted command. Change the cat's expression to happy. And yeah, it worked. The AI updates only that part of the image, fixing the issue precisely. And this is a huge win-win. The user gets exactly the result they want, and we get incredibly high-quality, actionable feedback that we can use to improve the model. This collaborative approach is really the gold standard for effective feedback design. Another great time to ask for feedback is when the model itself has low confidence about what a user wants. For example, if you ask it to summarize a paper, the model might be unsure if you'd prefer a short, high-level summary or a long, detailed one. Instead of guessing, a great strategy is to generate both options and present them side by side, just like you see in this example from ChatGPT. The user can simply review both and choose the one they prefer. This gives us a clear comparative signal. This response is better than that one, which is perfect for what's called preference fine-tuning. The main challenge, however, is that we are asking the user to do a lot of work. Reading two full responses takes time and effort, and we might not always get thoughtful feedback as a result. So to reduce that user effort, some applications take a different approach altogether. Instead of showing two full responses, they present just the beginning of each response as a partial preview. You can see this in action here with Google Gemini's drafts. The user simply clicks on the draft that looks more promising to expand and read it. In this design, the click itself is the feedback signal. It tells us which opening line or initial approach caught the user's attention. Now, there's healthy debate about which method is truly better. Do you get more reliable feedback from a user who has read the full text, or is the initial click on a promising start a stronger signal? It's a key design trade-off to consider when building these systems. So far, we've focused on the logic and architecture of the AI application itself. Now let's zoom out and look at the underlying infrastructure required to run all of this. in a real-world production environment. This diagram shows a high-level view of a typical deployment stack for a modern app. You don't need to memorize every box, but notice the key areas. We have experimental resources for development and pipelines, and separated production resources that serve the live application to users. This stack includes critical components like a data store, a vector database for our RAG system, a model registry to version our models, and finally, the deployment service that handles the traffic. The key takeaway is that a production-grade LLM system is a full ecosystem of tools working together to ensure reliability and scalability. The last diagram can look a bit overwhelming, so let's simplify it. We can break down the process of building a production LLM map into 6 key areas to consider. First, the LLMs themselves. Which models are we using? Are they open source? Are they proprietary? Then the data. What information are we feeding the models and how do we manage it? Third, a robust evaluation framework. How do we objectively measure if our app is good and getting better? Fourth, the serving framework. How do we deliver the model's responses to users quickly and reliably? Then comes the orchestration layer. How do we manage the complex workflows and agentic steps? And finally, it ends up with the auxiliary systems. This covers everything else like logging, monitoring, feedback, collection, etc. Thinking about a system in these 6 categories helps us put some structure for our development and ensure we are not missing any critical pieces. To make all these abstract concepts more concrete, let's walk through the full stack using a practical example. An AI coach or an AI tutor. Imagine an application provided by an LLM to help people practice for job interviews. As you can see from this mockup, it has a conversational interface where it can ask questions. It tracks the user's progress in different areas like data structures and system design, and it acts as an AI tutor. Over the next few slides, we'll break down how we would interact and build the specific applications, applying the patterns we've just discussed previously. Before we build anything, we need to know what it should do. Here are the functional requirements for our AI coach. First, it needs to ingest a syllabus or topic. It must be a conversational system, allowing the student to ask clarifying questions, go off topic, or even ask the tutor to critique their work. On the other side, the system wants to be able to generate pop quizzes and checkpoint the student's progress. These are the core features our users will interact with. Now let's translate these user-facing features into technical requirements for engineering. To build this, we'll need to support multi-turn conversations with both long and short-term memory. To answer questions about a syllabus, we'll need a knowledge storage and retrieval process, which points directly to our access to it. Of course, we'll need guardrails for safety, real-time inference for a good user experience, and to handle all the different tasks like explain or pop quiz, we'll need an agent-based system that can use function calling. We're not going to build this entire complex system at once. We'll follow an iterative and layered approach. We'll start with the simplest possible feature, just the explain function, and build a basic RAG system for it. Then we'll progressively add layers of complexity, like agentic behavior and more tools, and discuss the new challenges that arise at each stage. We'll wrap up by looking at concerns that apply to the whole system. For example, inference, guardrails, and model training. Okay, here's stage 1. Building the core explain functionality. This is our minimum viable product, and it's a classic RAG architecture. When a user asks a question, the orchestrator performs a similarity search against our vector database, which contains the syllabus content. The most relevant text chunks are retrieved and combined with the user's query into a REST prompt. This is then sent to the LLM, which generates the final explanation. This simple pipeline forms the backbone of our AI tutor. Even with the simple MVP, we immediately face important challenges. We have to make key tech stack decisions, like which embedding model and vector database to use. We need a good data strategy for cleaning and chunking our syllabus. And most importantly, how do we improve performance? Should we use a bigger, more expensive model, or should we consider fine-tuning a smaller one? To answer that all, we need a solid evaluation framework and a strategy for prompt engineering. Now let's enhance our system to handle most complex tasks by evolving it into an agent-based RAG. The key change, as you can see in the diagram, is that the simple LLM block is now an agent core. This core is more than just a text generator. It has distinct components for a task planner, memory, and an action executor. This structure allows the system to reason and break down problems into multiple steps. So, what exactly is an agent in this context? An agent is a system with complex reasoning abilities. You give it a high level task and it can plan and execute a sequence of steps to complete that task using a set of tools. We need agents because real world requests often require complex multi step workflows. Frameworks like React and the use of function calling are what allow us to build these dynamic systems. Let's see this in action with the React framework. Now, React stands for Reason Act. The agent follows a thought action observation loop. For a question about Newton's laws, its first thought is I should look at the database. That leads to an action using the RAG search tool. As you can see, it then gets an observation, the results from the search. It thinks again, I have the final answer, and then generates a response. This reasoning cycle allows the agent to intelligently decide which tools to use and when. Our agent is smart, but its only tool is RAG search. To make our AI tutor truly capable, we might need to give it more tools. We're now connecting our orchestrator to new capabilities like a code executor to run code. The ability to call external APIs like Wolfram Alpha and even other specialized multi-modal LLMs. This allows our agent to handle a much wider range of tasks. You'll also notice we've added a system for telemetry logs, which is critical for monitoring a complex agent. Let's see how our newly empowered agent would handle some of the required features. If a question isn't in its database, it can reason that it needs to use the search web tool. To save progress, it can use a checkpoint tool to write a long-term memory. And for a pop quiz action, it can call another system or API to generate the UI and manage the submission. This shows how agents can orchestrate complex multi-system workflows. Here are a couple more advanced examples. For a feature like critique picture, the agent recognizes it's dealing with an image and knows to hand off the task to a specialized multimodal model like Gemini. For a math problem like finding the 15th Fibonacci number, it can first generate the Python code, then use the code executor tool to run that code and get the correct answer, which is far more reliable than trying to calculate it itself. This powerful multi-agent introduces a new set of very complex challenges. We have to decide whether to fine-tune a model on how to use our APIs or just describe them in a prompt. We have to worry about the context length, manage, and version many different types of prompts. And verifying the agent's multi-step plans are correct is extremely difficult. Most importantly, as the agent becomes more powerful, the need for robust guardrails and alignment becomes absolutely critical. To address this point on safety, we must formally add guardrails to our architecture. As you can see, we've now inserted a guardrails layer that intercepts the user input before it hits the orchestrator. This layer is also responsible for checking the final output before it goes back to the user, acting as a primary defense for ensuring the safety and reliability of our application. The guardrail layer is essentially for any customer-facing app. Its job is to ensure safety by preventing toxicity, stopping sensitive data leaks, and keeping the conversation on topic. Critically, it also guards both inputs and outputs to defend against security risks like prompt injection and jailbreaking attempts. The trade-off is that these checks can add latency, but it's a necessary cost for a safe and trustworthy application. Our app is now functional and safe, but it also needs to be fast. This brings us to our next major concern: inference optimization. This isn't a single step in the flow, but rather a set of techniques and dedicated infrastructure that apply to all our model calls to reduce latency and improve throughput for a better user experience. So now, how do we actually serve these models quickly in production? The inference landscape is incredibly active, with many open source frameworks like VLLM, TensorRT LLM, alongside cloud solutions. All these tools are designed to serve large language models efficiently, using advanced techniques to achieve high throughput and low latency. Choosing the right serving infrastructure is a critical engineering decision that we have to make at this juncture. When we talk about performance, a key metric is perceived latency. We can improve this by streaming tokens back to the user, which makes the time to the first token a very important metric to track. Behind the scenes, the model serving frameworks use powerful techniques like continuous batching to increase throughput and speculative decoding to lower latency, sometimes even by a factor of 2 or 3. So far, we've assumed we are using existing models. But what if we need to go a step further and train our own custom model? This introduces a whole new complex offline process for model training, which then feeds the resulting models into our production system, typically managed through our model registry. I want to be very clear. Training a foundational model from scratch is a massive undertaking. It involves an enormous amount of work in data preparation, deep architectural decisions during model preparation, and the training process itself is a massive distributed systems engineering challenge requiring thousands of GPUs. This is a highly specialized and expensive process. And the challenges of training are immense. GPUs are scarce and expensive. Getting through high quality data is incredibly difficult too. So you're almost always better off fine-tuning an existing open source model rather than training from scratch. So after adding all these layers and addressing the key production concerns, here is the overall picture of a final stack. We have our core agent, which uses a RAG service and other external tools. It's protected by guardrails. Its performance is boosted by inference optimization, and it's powered by models coming from our offline training pipeline. We've systematically built our simple app into a robust, safe, and efficient production system. To wrap things up, I'll leave you with a few final thoughts. First, while LLM apps seems complicated, they might be engineered systematically. The data quality is paramount, but we also might want to focus more on faster inference and model safety. So remember that training from scratch is incredibly hard. For most cases, improving an existing open source model is the right path.
If you like this video, you will love what I have to say next. The 14-week Agentic AI program at Interview Kickstart helps engineers build real, career-ready skills. You'll work on 2 live projects with FAANG instructors and leave with portfolio work that actually makes a difference in hiring. Over 20,000 tech professionals have already trained with Interview Kickstart, with many moving into roles paying $300,000 plus. Want to learn more? Join the free upcoming webinar. Ask questions, meet the instructors, and see if it's a fit. Not ready yet? No problem. Start with the AI agent building videos here on the YouTube channel. We recommend this one. Either way, the key is to just get started.